Welcome to the webinar. Yeah, so why are we here and why do we want models for testing or in general for development and testing? That's the question. Let's start with one central thing that is important for modeling. Models give us the power of abstraction. So what is abstraction? Abstraction is you leave things away in order to understand a certain aspect of the problem better or of a solution better. So it's always about a certain aspect of something you want to understand. Let's have a look at an example. Here I have a number of matches. Yeah, please estimate it, the number of matches for yourself. Just to give you 2-3 seconds, maybe you can count them. So most people have numbers about 50, 70, some of them 200, some of them 30. So how many matches are there really? It's 123. So what happened here? Why are those matches in the second picture? Why is it so much easier to count them? Because I left away the information about the position, geometrical position of the matches. I reduced everything to a certain pattern. By that, I introduced a certain abstraction, and this abstraction is focused on counting the matches. For other purposes, it's not as good, or maybe it's completely irrelevant for other purposes, but for counting the matches, that's a really good pattern, a really good abstraction. Unfortunately, a real-world system looks more like that. To give an example, that's a generated diagram of all the dependencies in a motor control system. That's really huge, and it's a very well-designed system, but this flat world view on this system doesn't help at all. So we need abstraction here to understand certain aspects of our system. This holds for development as well as for testing, but we want to focus on testing now. So what's abstraction and automation with model-driven development and tests? Give you an example from the realm of software development. In the end, what we want is an executable application or an executable test case. That's usually an executable, a binary format, a hex format, or whatever I want to produce. This has a lot of details about the platform where I want to execute it, all the assembler code, instructions, and things like that. On that level, a human being has a hard time to work. So that's why we introduced high-level programming languages like C. They provide a certain abstraction that makes it easier for human beings to really develop, to express what we want to do. But it still has a lot of details about how do I want to do it. In this case, that's a switch case statement. It's already better to understand than the executable below. By the way, it's really the real executable of a STM32 program, and it's the same program in C. But what I really want to express is, or understand is, what am I doing here? So not how am I doing it, or how do I explain it to the processor? So what do I want to do? In this case, I created a ping pong or a blinker, something like that, that turns a LED on and off. So by using this model, this state machine model, I have a much higher level of abstraction, and I can focus on what I want to achieve and not on how I do it or how do I explain it to the processor. So what happens here is we have an abstraction between the executable and the C program, and we have another abstraction between the C program and the model. Yeah. So essentially, that's those are two different levels of abstraction. So now if I work on that level of abstraction on the model level, I still in the end have to produce an executable. So what do? I use an interpreter or a code generator. In this case, in this example, I have a code generator that generates from the state machine model a piece of C code. and the C code is compiled into an executable. So, and we add the information we took out before to have this abstraction. We add it by automation, by generator or by compiler. So essentially, a model is just another abstraction on top of a regular programming language. It doesn't have to be graphical. It can also be a textual model. It can be any kind of table or diagram or whatever you want. The essential point here is it needs to be an abstraction. Doesn't matter whether it's graphical or not. Graphical models help because we are really able to grasp things much faster in many cases with graphical models, but a model can also be textual. So on the right side, abstraction, on the left side, automation. So that's how abstraction and automation works with model-driven development. That's very generic, also for not only for tests, but also for development. So let's have a look at the different levels where we want to test our embedded system. Now, let's assume we have an ECU with a microcontroller, with power electronics, sensors, actuators, and in the end, we want to control a motor with a pump and a hydraulic system, for example, a lubrication pump or hydraulic pump or whatever it is. No? So we want to test this. Usually, many teams start with unit tests. With a unit test, you test single C modules or classes. That's easy to do. That's very fast. You can write fast tests. It's really easy to automate and so on. If you bring together several units, it's already called a software integration test. You can still use a unit test tool for doing that, but you cannot test all the units, especially in an embedded system. It's hard to test, for example, a motor controller or battery controller because they're highly concurrent, asynchronous, and so on. On the next level would be the smallest possible hardware-software integration test or the smallest possible hardware in the loop test. For example, if you take the microcontroller with the complete software stack and the drivers as a black box, you can use this black box to run as hardware-software integration test. The next level would be a big hardware in the loop test that already contains much more of your ECU or the complete ECU with the power electronics, with sensors, actuators, and so on. And the last level here in this example is a system test where you actually really bring the rest of the system, so the system you want to control, also in the test loop. So you put in the motor, you put in the pump, you put in the hydraulic system, and you run a system test. All test levels make sense. Usually you do not use all the tests on all the test levels because it's a lot of effort to test on all the levels. But I guess that's a pretty complete picture about dynamic software testing for embedded systems. So the unit tests are fast. You can run them very often on every commit, on every change. They're inexpensive and they are really easy to automate. From top to bottom, it gets slower. You do not execute them this often. It gets much more expensive and it gets much harder to automate. So what can we do to enable a team or a software development team with models to help make the development of the tests faster here? So what do we need? First of all, we need a test harness for the system under test or for the component under test. So a test harness has two things. First, we need test cases. That's obvious if you want to test. The second thing is not so clear to everybody. We need to satisfy the interfaces of the system or the component under test. That means we need to satisfy with stubs and mocks, for example, the interfaces of a C component, or we need closed and open loop simulations to simulate the environment the component controls. So for unit tests, they are usually synchronous, so we need synchronous test cases. And usually we get away with stubs and mocks. That's pretty simple to do. There are frameworks to do that. And so you need to satisfy the interfaces on a C level, for example. For integration and system tests, you do not get away that easy. You need asynchronous test cases. So asynchronous is much more difficult to do, asynchronous testing. And usually you need closed or open loop simulation. I'll give you an example in a minute. So you need the simulation because if you start a system, the components need to be there. If not, your system fails immediately and you don't even get to the situation or to the state where you actually can test something. So you need more than just test cases. No, two things: test cases and simulations or environment stubbing, mocking simulations. So what can you do with a hardware-software integration test? Unit test, I guess everybody's familiar with a unit test. Hardware-software integration test, not everybody's familiar with that, or also with hardware-in-the-loop testing. So the main goal is here, for example, not to test the motor control, but the integration of the motor control with a software system, including drivers and an electrical system. By using simulations, you can put your system in almost any state to test it, for example, by changing the simulation for failure injection. And by doing that, you can automate the testing very good. So let's have a look at the black box microcontroller. For example, if you want to test the shutdown path for temperature, you need to stimulate the ADC, for example, by providing an analog value at the pin of the microcontroller. Then the changed value cascades through the system. All things are happening in parallel. That's why you need asynchronous test cases, not only synchronous test cases. And the motor control needs to work. So for the motor control, you need the environment simulation, or for other components like battery and so on. And in the end, what you expect is that, for example, the motor stops after 100 microseconds by shutting down the PWM, or you get a certain CAN message that gives you that tells you that the system detected the problem correctly. An example for a motor control system for a plant simulation would be, in this case, a BLDC motor with 3 PWMs and block commutation. In one direction, the motor control generates PWMs to control the motor, to stimulate the motor. And now, if you do not have a motor on this side, the motor control does not work. So you don't even get to the state where you actually can test something. So you need either a motor or a plant simulation. If you have a plant simulation, a motor simulation, the simulation measures the PWMs, calculates the new speed of the model, of the motor, and generates the signals in the same way the real motor would generate the signals. So by doing that, you have satisfied the interface and the closed loop expectations of the motor control system. And now you can actually really run your software and bring it into any state you want. So you need, in most cases, you need some kind of closed loop or at least open loop simulations to test embedded systems on a higher level than unit tests. So how do we do this? I give you some examples for test case models for test case definitions, and some examples for models for environment simulation. So again, those two things. So first example for a model, you could use a classification tree for a structured development of test cases, for example, to derive equivalency classes, to make border analysis or other situations. It's a very nice and structured approach to derive test cases from requirements or from situations, from use cases you want to test. So it also helps with analysis for safety relevant systems, because you can use the classification tree to break down your system in smaller parts, analyze them, and come up with test cases for them. There's, for example, a tool like Tessie you might have heard of, or you might use, that uses this method to help with the derivation of test cases. So you can generate, for example, test cases directly from this diagram. The second example I want to give you is a state transition test. That's a very nice structured method for, especially for asynchronous integration level or system level tests, but you can also use it for synchronous testing, for unit testing, for example. The idea is you describe the black box behavior of the expected system behavior. And from that, you derive the needed test cases to cover the happy and unhappy paths in your system, in your component or in your integration case or in your system. It's very nice for robustness test, and you can derive a lot of test cases very fast. So a really nice method. So the last model technique I want to show you are sequence diagrams. They're really nice to describe and document test cases. It provides a very nice graphical view on test cases and test execution. So not only can derive or you can not only model test cases, but also if you transform the generated or the results of your test cases again into those diagrams, you can have a graphical look on the executed test cases, and by that learning what your system did wrong and so on. So it's easy to understand also for non-developers and non-testers. So if, for example, if you're talking on system level testing, not everybody is a developer or a tester that understands the software part of your system. So those diagrams are usually very nice to discuss on a system level with a system expert, for example, or with somebody who provides requirements. So those three methods can be used to define test cases, and if you have the right tooling, also generate test cases directly from those diagrams. Let's have a look at the environment simulation. So just to say it again, those methods can be used on all test levels. So unit test, integration test, system test. For environment simulation, usually you do not use environment simulation on a unit test level. It's more on an integration or a system test level. So two examples for models that are very useful are, first of all, state machines. State machines are a very nice method to define the environment simulation for state and event-based systems on a very high level of abstraction. Also very good for code generation, very easy to generate code from a state machine. And the second example I want to give you is a data flow modeling. I'm sure many of you have heard or are using MATLAB Simulink. That's a typical data flow model. And with those data flow model, you can model continuous behavior or closed loop systems. So for example, a motor simulation you would rather do in a Simulink model or a data flow model. But for example, a state-driven behavior or an event-driven behavior, communication protocol or things like that. Also, in many cases, battery management system, some things like that. You can model very good with state machines. So now we have models for environment simulation, and we have models for describing test cases. By the way, there are many more approaches to model-based testing. I only can give you a couple of examples here. Now let's have a closer look at the state transition testing. We start with a piece of paper. So you can actually use it on a piece of paper and derive test cases there. So you design the black box, expected black box behavior of your system under test as a state transition diagram. So for example, first you want to bring the system into motor off, then into motor on. From here you could brake and change the mode, or you could you could change the speed, stop it, and then change the mode. then you could change to mode 1, mode 2. So that's those are all possibilities you could test. Some of them might be errors, some of them might be happy paths or unhappy paths. So that's completely up to you, what you want to model. The idea is now you take this diagram and you think about what do I need to test. So every way between the initial point and initial and end is, so every path is essentially a test case. That's the idea. So for example, test case 1 is one path. And now we see that we did not cover the other path here. So to cover the other path, I need a second test case. So with those two test cases, I have covered all transitions and all states. But what I did not cover in this case is, for example, here the blue path. And when I want to run this blue path with mode 2, that's something I did not cover. So the combination of those two modes I did not cover. And for that, we can introduce a metric. And we can use this metric to, for example, to generate this test case 3 and test case 4. So the green and the red one, they combine the different parts of the path with each other. And it gets much more complex, or you get much more test cases if you introduce cycles or if you introduce more possibilities here. And at a certain point, it gets very useful to have a tool that actually supports you in generating the test cases from those diagrams. So for the simple state transition test, you can do it on a piece of paper. More complex situations, you need some tooling. I'm going to show you how that's done. In our case, we use a test model. We define this test model as a state transition test. And from that's what you do. That's your black box behavior you expect of your system. And we generate not only the diagram of all the test combinations of all the test paths, but we actually really generate the test cases that are executable directly from this model. So that shows pretty good the power of abstraction. It's much easier to produce the diagram on the left than to create 15 test cases. And if you turn up the metric a little bit, you get much more test cases, or you need much more test cases, hundreds of thousands of test cases to really get a good robustness test or something like that. And that's usually not done manually. In most cases, not. So I give you a little example based on our mini-hill test system. That's a little hardware in the loop test system. That tests a microcontroller with a complete software. So it's the smallest possible hardware in the loop test on your desktop. That's I have an example here. So that's my setup here. That's the system under test, STM32 in this case, microcontroller with a motor control software. What we do is we model the environment simulation and the tests. We generate the C code, compile it, flash it to the test system, and then we run the test cases. Again, we log the test execution, and then we transform it again into models, or at least into high-level diagrams or spreadsheets or something like that, for us to understand better what happened in this test. Here you see, for specification, you can use sequence diagrams, state machines, and so on. And for the results, you can also see the results as sequence diagrams. Very useful to understand what happened there. So then you learn and iterate. So just to introduce the example, the system under test I'm going to show you is a microcontroller STM32 with a motor control software. It generates the signals to control the motor. The motor simulation runs on the hardware loop system here. It generates the whole signals, and so the motor controller runs in a loop with the not against the real motor, but against the simulated motor. Then we simulate the temperature sensor, for example, to simulate different errors, temperature errors, shutdown, and so on. And we have a UART line to control the test, the system under test, to start the motor or to change the speed and things like that. So now I'm going to demonstrate you the state transition test in our model-based development environment. Just to explain you what you see, everything inside this box goes into the test system. So that's the system under test. That's the test system. So here you have the environment simulation and the test cases. So in order to test, of course, we need the IOs. So we measure the duty cycles. We have digital, analog IOs, and so on. On that level, we have the motor simulation and the temperature simulation. And here we have the test cases. So for the test harness, we need the simulation elements. For example, the motor simulation is in this case state-based, event-driven simulation with a state machine. We can model the state machine, and for example, here in this case, we calculate the speed, and then we generate the whole generator generates the signals needed of the motor control to control the motor, to work with the motor. That's a state machine. You can use the state machine for the simulation. You could also use a Simulink model, generate the code and integrate it here. For example, for a field-oriented control or so, I would not need use a state machine. I would rather use a Simulink model or a data flow model, or a Scilab or whatever tool you want to use there. So the last thing you need is the test case. So let's have a look at the behavior of the test case here. In this case, that's also a model, but it's a textual model. And we turn it around. We do not model the graph and generate the code or the test model. We do it the other way around because it's much more efficient. For example, I model here all the test steps, and we derive whatever we change, we derive the model, the graphical model. So we derive the sequence diagram. Actually, that's not an abstraction, but it's a graphical view of the same test case here. It's very nice because it's much faster to work on a textual level than on a graphical level for this kind of problem. For state machine, it's much easier to work on a graphical level. For sequence diagrams, it's actually much faster to work on a textual level and derive the diagrams from that. If you go one level up, for example, here you introduce sequences based on those steps. Here you see we make the sequences flat, because the hierarchical system you have here, and here we have the flat world system to understand better the context of the test cases that are executed. So actually, in this case, you can see how valuable models are to analyze a situation. And last but not least, our state transition tests. So here we have, based on those test steps and sequences, you can describe state transition tests. So those state transition tests, again, from initial to end, you have all the, we want to cover all the paths. So we change the speed to 10%, 50%, 90%, and then we want to run all those different paths as test cases. So for example, if I want to add another path, for example, from motor stop to directly to motor running or to brake, for example. So I have a motor stopped here, and I want to go directly to brake. While braking, activating the brake and testing the brake, now I have one more test case here, or one more path I need to cover. So most likely I need 3-4 more test cases to cover this in combination with the other things I did. So let's go back here. In this case, I activated the metric and switch 1. That means I want the combination of all the inputs and outputs, or all the paths around one state. I can raise this to 2, 3, and so on. So let's have a look at what happens now. Now I have the system here running. That's I flashed the test cases and the environment simulation here. Here I have the system under test. So let's I'm connected now. Let's start the test here. Here you see the regular tests, and here you see the combinatorial tests, so the model-based tests here. So I run through. So if I pull a plug, was too late. I'm running the test cases again. So I pull a plug, and now you can see that it fails, and I put it in again, and so I just took away a signal to show you that it's live. And here in the end, you get, for the errors, you get again the recorded sequence diagram. And I can click on it, and in the background you see the editor changed to exactly the step where actually we had the problem. So those diagrams help very good in identifying what really happened and where do I need to look in my test case. And here, for example, if you have a history before the error happened, a lot of things happened before, then you see exactly what happened before. So that's something where models really help. Now to give you a last little example of the power, I can generate the documentation to show you a little bit what happens. So now just a second here. Yep, here that's the documentation. That's the state transition test I have shown you, and those are the generated test cases. So now if I change the metric, for example, to n switch 3, that's just one number. And now I regenerate in this case, the documentation. I could also directly generate it, flash it, and run it, but it takes much longer now, or at least the test execution, because it's you will have much more test cases. So now I reload the documentation, and you can see from the same diagram, I now generated something like 67 test cases. So you can imagine that's very useful to provide robustness tests for embedded systems, and it's completely asynchronous. So we can run asynchronous tests on asynchronous components. You can run tests in parallel and so on. And this actually would be really hard to achieve with pure C code or with normal programming languages, with normal programming language. That's much easier to do with models. So that's it from the demo. I'm at the end. To give you a brief conclusion, models for testings help you to work on a higher level of abstraction, to understand and communicate problems and solutions better. And you can also use them to derive and generate test cases in a more structured and efficient way. This altogether speeds up the development of the environment plant simulations as well as the test cases. So if you have any further questions, don't hesitate to contact Michael Weiss from Hitex or myself from PROTOS. Thanks for your attention.